Good afternoon to each and everyone. I'm here to present our research entitled Neugad, a neural machine translation for English to Yogad language. The researcher are Rod Ian L. Tobias, Jerilan Bigarnase, Angel P. Roduta, and yours truly, Kating Glen Feliciano. The language barrier prevents the exchange of ideas, limits access to information, and isolates individuals and communities. The Yogad language is an endangered indigenous language spoken by the Yogad tribe in Isabela province of the Philippines, particularly here at Echage, Isabela. The Yogad language is primarily used for intergroup communications but not actively transmitted to the younger generations. Therefore, we come up with this technology, Yogad, a neural machine translation for English to Yogad language. The objective of this study is to demonstrate the feasibility and effectiveness of employing neural machine translation (NMT) algorithms in the design and development of a machine translator system. Specifically, this study aims to design and develop a machine translation system, implement a transformer model for the neural machine translation algorithm, to develop a machine translator system for Yogad and English language, train the translation model using a parallel corpora of Yogad and English text data by exposing the model to align linguistic example, and to evaluate the quality of the developed neural machine translation system by comparing its output to reference translation using established metrics like the bilingual evaluation under study, the Blue and Yogad expert. This study was developed through utilizing or using the Rapid Application Development RAD. And to achieve the following objective, the following steps were uh, proceeded in product design and development. It began by collecting the parallel corpus of Yogad and English sentence, encompassing a diverse range of topics and contexts serving as a data set for training the model. Following with this, the implementation of the transformer model to NMT algorithm for parallelization capabilities, scalability, and effectiveness in capturing long-range dependencies in a sequence took place. Subsequently, the NMT system underwent evaluation using established metrics such as the BLUE, which measure the overlap between the system generated and the reference translation. Additionally, uh, domain-specific expertise represented by a yoga expert in this case contributed to the evaluation, ensuring that the system effectiveness in specialized domain. The feedback obtained from the evaluation metrics and expert assessment inform fine-tuning iterations to enhance the translation quality. This iterative process continued until satisfactory performance was achieved, ensuring that NMT system is suitability for diverse linguistic contexts, including specialized domain like the Yogad. Next is performing inference testing on the dataset using the trained transformer model by generating translations in the machine translator system for the test data to assess the system output quality. And lastly, the system was ready to deployment, but before that, thorough testing of the machine translation system was conducted in a production, like environment identify and address any issues that may arise during the deployment. This figure is the system architecture. The different processes of the application of the NMT algorithm, particularly using the transformer model with the dataset. The data preparation for NMT from English to Yogad language was crucial step to ensure the effectiveness of the model. The first phase of this process involved standardization, wherein the raw data was cleaned and formatted to maintain consistency and coherence. This included handling punctuation, special character, and addressing any spelling or grammatical inconsistencies present in the original text. The standardization ensures that the input data was uniform and facilitated smoother training for the neural network. The next step was tokenization, a process in which the text was broken down into smaller units, typically words of subwords units. For English to Yoga translation, this involved identifying the segmented words in both source and target languages. Tokenization played a crucial role in capturing semantic, linguistic, unique to Yoga. Once tokenization data was then vectorized, the meaning it was converted into numerical vectors that the neural network could process. This involved the representing each token into a numerical vector, embedding the words or subword units into a continuous vector space. Embedding this captured semantic relationship between words, allowing the model to grasp the context of the input and generate accurate translations. For English to Yoga NMT, specialized embedding technique were applied to capture the linguistic characteristic of the Yogad, ensuring that the model could effectively learn and represent the language-specific features. The foundation of the transformer lay in its innovative attention mechanism, which enabled the model to focus on different parts of the input sequence when generating the corresponding output. The third phase of the English to Yoga MT process is training the transformer model took center stage. So during training, the model learned to map the input English sequence to their corresponding yoga translation by adjusting its parameter through an iterative optimization process. This involved exposing the model to a large set of paired English to yoga sentences and calculating the translation errors and updating the model weights using back propagations and gradient descent. The training phase aimed to minimize the translation loss, ensuring that the model became adept in capturing the intricate linguistic patterns and between the two language. Lastly, the evaluation of the English to Yoga neural machine or MT model involve a comparison between the expert evaluation and the blue score. The expert evaluation typically involve human linguistic or the native speaker assessing the quality of the model translations based on linguistic accuracy, fluency, and overall coherence. On the other hand, the blue score was quantitative metric widely used in machine translation tasks, including the NMT. This is the result and discussion of our research. This is a developed English to Yoga machine translation system wherein once you click the button translate, it will translate uh, the the word you have typed or want to learn. Let's say for example here, they type eat the rice. After clicking the translate, it will translate the English to Yoga. So this is a sample translation. And upon implementation of the transformer model of neural machine translation algorithm to develop a machine translator system for yoga English languages, this pseudocode outlined the implementation of positional embedding layer. And next, this is the pseudocode for constitutes critical components for the attention mechanism with transformer architecture. So this is essential in natural language processing tasks. It comprises three functions, the shape list, attention mask, and the mask attribute weights. And this is also the pseudocode shows the operations of scale dot product attention mechanism, a foundation for component in transformer architecture. Next, this is for attention mechanism. So this pseudocode above define the structure of multi-headed attention class. And this is the pseudocode for encoder. Represent the pseudocode outline the structure and functionality of transformer encoder class, a key component in the transformer model architecture. And this is the decoder pseudocode. So this class is initialized with parameters including embed dim, and this part, the transformer decode design emphasize the effectiveness utilization of set, self-attention, and cross-attention mechanism. enabling the model to capture both local and global contextual information. This part is setting up the transformer model pseudocode. So the overall architecture is consolidated into a TensorFlow model that takes both encoder and decoder inputs and outputs the predicted target sequence. And this figure is the data from the CSV file was read that the code read the data and creates a source column, preprocess the target column by adding start and end token, removes unnecessary columns, and finally display a sample of process data. The result in is a data frame suitable for training models that generate sequence such as machine translation models. Then this figure shows the list of tokens generated by a BERT or bidirectional encoder representation from a transformer or tokenizer. This is the train the translation model using parallel corpora of Neugad and English text data by exposing the model to a line linguistic example. So this figure above shows the training progress of neural network over multiple epoch, displaying the key metrics such as loss and accuracy for both the training and validation sets as well as the learning rate. Considering the broader aspect, the absence of significant gaps between training and validation, metrics such as lack of overfitting, the model appears to generalize well, capturing patterns from the training data without memorizing them to the extent that it fails to perform on new data. This aligns with the primary objective of developing a model that not only performs well on training data but also exhibit robust generalization. This figure given is to evaluate the neural machine translation. So this is the result. Quality by comparing its output to reference translations using established matrix like bilingual evaluation. So this figure the blue score obtained the machine-generated translation, specifically 0.4239 or 42.39% falls within the range categorized by Google Cloud Translation Guidelines. According to these guidelines, a blue score in this range is typically associated with translation considered to be understandable to good quality. And to evaluate that neural machine translation system quality by comparing its output to reference translation using established matrix like bilingual evaluation under Study Blue and Neugad expert. So this is the result. Yeah. And this table represent the comparison between human translation and the model-generated translations evaluated through Blue scoring and expert evaluation scoring for different n-grams. At 1 gram level, the model performed well, achieving perfect Blue scores and expert evaluation scores for most example. However, a discrepancy arises in the translation of the word house, where the model-generated translation I am does not match on the human translation binalay, resulting in a Blue score of 0 and an expert evaluation scores of 0, moving to the 2-gram level. Differences between human and model-generated translation become apparent, leading to lower Blue score and expert evaluation scores. Notably, the translations for long pants and hard rock fall short, resulting to Blue scores of 0 also and expert evaluations scores of 0. To the evaluation across n-gram level reveals both commendable alignment and notable discrepancies between human and model-generated translation, emphasizing the importance of elaborate assessment for achieving accurate language representation in machine translation model. And for model testing evaluation, this is the accuracy evaluation table. The table above presents the evaluation result of the translation model. It presented a structured table providing insight into the model performance across the different n-gram level. So, for the 1-gram level, the model demonstrates a high level of accuracy, reflected it to be substantial blue score of 90%. Notably, the model excels in translating individual words accurately by achieving also 90% average expert evaluation score. And according to Google Cloud Translation Guideline, the blue score of 90 falls under a category of high quality translation. At the 2-gram level of blue decreases to 40.20%, suggesting a moderate level of accuracy in capturing two-word sequences. The expert evaluation score aligns with the observation, registering a 45%. The computation of the average evaluation per score for 2 gram is that. And for the conclusion, the graphical user interface or GUI, which emphasize user-friendly interaction, effectively showcase the design and develop of the machine translation system. Using the sophisticated NMT technique, the well-designed interface make it easier to enter English source material. Figure 6, the figure illustrates also that the dynamic capabilities of the system, which shows off its expertise in real-time translation and give user an easy-to-use platform for linguistic modification. Under the implement of the transformer model, a crucial component of NMT algorithm is thoroughly detailed in the provided pseudocode. A key elements such as positional embedding, attention mechanism, and encoder-decoder architecture are systematically presented. The code outlines the complex process associated with multi-head attention, which help the model recognize various patterns and dependencies in input sequence. The complete transformer model setup procedure is described, emphasizing the importance of hyperparameter selection and sequential information assimilation through positional embedding. And another conclusion is that the process of training and translation model is explained in detail, starting with the analysis of parallel corpora of text data in English Yogad, which was shown on the result and discussion, and the token distribution analysis, to enhance the model comprehension of intricate language structure. The BERT tokenizer breaks down words into subword units, was demonstrated by word piece tokenization, which was shown also on figure 9 on the result and discussion. The evaluation of the neural network translation system is conducted through comprehensive analysis utilizing both automated metrics like blue scores and human expert evaluation. Under the result and discussion, the blue scores for different n-gram orders providing quantitative measures of translation quality. The detailed breakdown of blue scores for individual n-grams accompanied by a sample translation analysis allows for an in-depth comprehension of the system advantage and disadvantage. The comparison between model-generated translation and reference translation, as well as the assessment of different n-grams level, highlight the system proficiency at the human unigram level, but also points to area where improvement is needed as the n-gram order increases. And this is the recommendations. Expanding the training data set with more diverse example and incorporating domain-specific content could enhance the model understanding and improve translation accuracy. To implement iterative fine-tuning of the model with a particular emphasis on capturing and reproducing intricate linguistic structure. Special attention should be given to refining accuracy at higher n-gram level, ensuring more uh, and contextual accurate translation of yogurt sentences. And given the challenges in maintaining accuracy, as the n-gram level increases further the research of on the linguistic characteristic of yogurt, especially focusing on its unique features and expressions, can contribute to the development of more contextually accurate translation. And thank you for listening.